Hey everyone, so today we'll talk about completion of metric spaces. So let's assume we have a metric space X. So it's a metric space, so there should be a distance function. So what's a distance function? Well, it's nothing but it calculates the distance between 2 points. So you have X and Y. This will be a positive number, right? It's bigger than or equal to 0. Moreover, it will give you a kind of measure for distance, right? So you basically have three properties. So first one is that this should be a function from the space X to positive real numbers, and it should have the symmetric property. So that means distance of xy should be equal to distance of yx. So it doesn't matter how you calculate the distance. If you calculate distance from x to y or distance from y to x, it's the same thing, right? And the third thing is the third property is that the triangle inequality. So when you have distance of xy, well, it's less than or equal to distance of xz plus distance zy. So z is any other point in the space x, right? So this is a triangle inequality. Now, if you have a function on the space which satisfies these three properties, then that's a metric, and so we say this is a metric space, right? Okay, so that's a metric space. Now, the important thing that we want to have for the space is that we want this to be complete, right? So what's completion? So what's a complete metric space? Complete metric space. Okay. So as the name indicates, it's a complete, right? So it's kind of like it's a complete space. Okay. So what does that mean? So in analysis, you have this concept of Cauchy sequences, right? So what are Cauchy sequences? Well, let me write it down. So we say xn is a sequence in this space, right? So you have a space. Now this is a sequence in the space. That means you have, you're just mapping points. So x0, x1, x2, x3, etc. Right? So it's as if you have mapped 0 is this one, 1 is x1, 2 is x2, 3 is x3. So you have a sequence in this space, and you have a property that this is a Cauchy sequence. What does that mean? If you take the distance of two points in the sequence, so xn and xm, right? You can actually bound this by epsilon if you take n and m sufficiently large, right? So if your n and m are extremely large, right, that means you have n and m bounded below by n. So there's a big number n. If you pick n and m larger than that, the distance between xn and xm can be bounded above by epsilon, where epsilon is in your control. It can be any small number that you want. Well, the way I want to visualize this is as follows. You have maybe x0 is here, x1, x2, x3, it keeps going, and then let's say for very large number xn, and xn plus 1, and then xn plus 2, and then xn plus 3, and then xn plus 4. So what's going on here is that initially x0, x1, this is the distance between them, x1, x2, this is the distance, x2, x3, this is the distance, but ultimately you will be able to find a number beyond which all the terms, the distance between them is extremely small. You can bound that by epsilon, right? So all the terms, not just the consecutive, but all the terms beyond the capital N, they are bounded above by epsilon, right? This is possible. So this is kind of a visualization of Cauchy sequence that ultimately you will be able to, compress the terms, right? The terms will be extremely close to each other. Like here, I'm just showing you the consecutive terms, right? But not just consecutive terms, but any terms beyond a point, they are all closer. And so what happens is that in a complete metric space, if you have this kind of sequence, Cauchy sequence, it actually converges. It will converge to a point X, right? So that's the property of a complete metric space. So in a complete metric space, if you have a sequence of this sort, it will converge, right? It will converge to a point X. So what does that mean? Can I have this metric space XD to be inside another space right? Let me denote it like this, x hat d hat. That means there's another space x hat, right, which has this metric space embedded in it. Like there's a image of this metric space inside the space, and there's this another metric d hat, right? To be more precise, let me explain what embedding means. Is as follows. So you have xd, you have this another space, a bigger space, let's say like this, okay? And what can happen is there is an image of this metric space inside this bigger space, right? So there's an exact copy of this particular space here, our metric space, inside this larger space. So what that means is the distance between any 2 points on this metric space is the same here, is the same distance, right? If you measure the distance xy, that will be the same inside this space, right? So in this space, the metric is different. It's d hat, right? So there's a copy of x here, right? There's a copy of that x here. So it's x. Let me denote it x tilde. Y, for y, there's a copy here, y tilde. If you calculate the distance, it's the same, right? So it's as if you have an image of our metric space xd inside the bigger space, and the distances are preserved, right? So it's the same distance here and here, okay? And moreover, it's a complete, right? So you're getting an extra property here that there is an image, and also it's the whole space is complete. That means if you take Cauchy sequences, it converges. But the problem is, if we try to pick a sequence, a Cauchy sequence from the original space xt, as follows, maybe it does not converge, right? The limit does not exist here, right? So here it's Cauchy, but limit does not exist, right? There is no limit here, or you cannot find the limit. But here xn is Cauchy, right? Implies the limit exists. Limit exists. Okay, so there is a limit for sure here. And it doesn't matter if you're picking sequences from the original space xt, or maybe some other sequences from this outer portion, right? It doesn't matter. If it's Cauchy, it converges, right? It converges. So that's the property of this bigger space x hat d hat. Okay, so that's completion. So this is this whole thing is like completion. If you have completion, it's good. We'll see later why that's the case. And then we'll look into specific cases of spaces and how we can make it complete and all that. We'll look into that later. Okay, so that's the setting. Now the question is, okay, this is like an abstract thing. Is it even possible to do this completion, right? That's a question. Is it even really possible for me to, have any metric space, and can I complete it, right? Is there a space like this where you can like embed it and it's complete space? Is it possible? The very interesting theorem is that yes, this is possible. So given any metric space, right, there is a completion. So it's xd is a metric space, then implies there is a completion. So there is a completion. Something like this, right? So the question is, how do we find this completion for any general metric space? Well, that's the cool part, right? So for any metric space, you have a completion like this. And the proof that we are going to look into right now is that how do we construct this space, right? It's going to be a big, there's going to be a lot of steps, and it kind of maybe get messy, but that's fine, right? We'll go through it. We'll see the proof for once, which maybe will be very helpful for us later if you're doing some other theorems or some other results that we want to use. Maybe we can use this particular result, and things will become easier for us. Okay, all right. Okay, so before I jump into the proof, I'm just going to give you some intuition behind what we are going to do next, right? So this is our metric space, and the problem is that even if you pick Cauchy sequences here, it does not converge, right? So some of those Cauchy sequences, or maybe all of them, they don't converge at all, right? That can be the scenario. Then the proof of constructing this particular completion space is all about giving limits, or providing limits to those Cauchy sequences, right? So if you pick xn to be a Cauchy sequence in this metric space, then you are providing the limit to this Cauchy sequence, right, as x naught, right? So that's what we are doing. But the problem is that you cannot do it for every sequence, right? The reason being, there can be some sequences which are at the end almost the same, right? So maybe like it started off as x1, x2, x3, x4, and so on. And as your n becomes larger and larger, it tends to maybe become some other sequence. For example, let's say yn plus 1, yn plus 2. Let's say y0, y1. Okay, this should be, I missed a point. I missed a point here. It's x2. This is y2, y3, y4, right? And finally, it's yn plus 1, yn plus 2, right? So, this can be one such scenario. The sequence xn, and there's a sequence yn. Well, they are not different altogether at the end, right? In this particular case, well, you should provide the same limits, right? If you're assigning the limits to these two sequences, they should be the same limit, right? So maybe y, right? Something like this. You should provide the same limit. So these are kind of problems which we need to address if we are assigning limits to these sequences, right? So that's the, the problem that we have. And how do we deal with this? Well, we have something called equivalence, right? Equivalence relationship. Okay, so what we are going to do is we are going to look into the space of all the Cauchy sequences, right? So we are just going to focus on Cauchy sequences in X. Okay, so all the Cauchy sequences, and we are going to use equivalence relationship. Equivalence relationship. Okay, we are going to, relate two sequences. Maybe these two sequences, x and yn, well, they are not altogether different, right? At the end, they become almost the same. So you want to say that these two are related, right? Similarly, you want to define a relationship where you're kind of group many of these sequences together into different classes, right? So you have this entire space of Cauchy sequences. And what you're going to do is you're kind of find relationship between sequences, and you're going to group them into disjoint classes, right? You're just going to break this entire Cauchy sequences, the space of all Cauchy sequences, into different classes, right? So using this equivalence relationship. Well, maybe many of you don't know what equivalence relationship is and how that gives us this breaking down of this entire space into disjoint classes. Well, you can look it up in any set theory, any book on set theory, or any book which deals with this concept of equivalence relationship. You can easily find the proof of this particular statement. Okay, so we'll just take that. If you have an equivalence relationship, then that breaks the entire space into disjoint classes, right? This is something which we are going to use now. Okay, so now the question is, how do we find that equivalence relationship between these Cauchy sequences?